Hi, and welcome to Mr. Crow's Classroom. Today we're going to take a look at radical functions and how to find their inverses. So let's check it out. Okay, first let's go ahead and remind ourselves what is the inverse of a function. Well, if I have function f of x, then we say f to the negative 1 of x is the inverse of f of x if I can plug f to the negative 1 of x into f of x, so the inverse into its original, and get x back. And I could do it the other way around as well. I could plug in the original into the inverse and I should get x as well. And the way you can think about this is graphically speaking, if I graphed f of x and f to the negative 1 of x, or the inverse of f of x, then they would be reflected over the line y is equal to x. And in essence here, on the left-hand side, you're getting a y value is equal to x for both of these. So essentially what you're deducing this down to is y is equal to x. Okay. Anyways, so that's how you can always check if one function is the inverse of another. Go ahead and plug them into each other, and you should get x back. Now, in order to find the inverse of any function, it's pretty straightforward. You're going to go ahead and flip the x and y variables, and then you're going to solve for y. And then that's it. Once you have solved for y, then you have found the inverse of that function. However, it is worth noting that not all functions have inverses. Also, you're going to notice something about that there's a little bit more to this, such as the domain and range restrictions, as you're going to see a little bit later. All right, now in order to accomplish this, we're going to go ahead and just review really quickly our square root, cube root, and nth root operations. So of course, if I take the square root of something, say x, then we'd use this radical sign with an index of 2. However, if there's no index listed, then we assume that it's an index of 2, so the square root. This can also be written as x to the 1/2. All right, and if we want to undo the square root of something or do the opposite operation, then we would square that thing. All right, and once we do that, then whatever's on the inside will pop out, in this case, x. Now, for a cubed root or an index radical with an index of 3 or something to the 1/3 power, then we would simply cube both sides to undo that, to pop out whatever's in the middle here. And then if we have the nth root, generically speaking, or to the 1/n power, then we can take that to the power of n, and whatever's on the inside will pop out there, okay? Because these are all inverse operations of each other. Now let's go ahead and look at this the opposite way around. So instead of starting with an square root, right, then let's start with an x squared, because we're going to have to be going back and forth a little bit today. And it's really important for us to understand this. All right, so if I'm starting with an x squared, then the opposite operation would be the square root of the square root. To pop out that x. If I have a cubed root, then it's going to be, if I have something cubed, then it's going to be the cubed root. If I have something to the nth power, then it's going to be the nth root. However, there's one really, really important thing we have to understand here, is that these are not actually complete. We actually, for all even indexes, we actually have to take plus or minus. Okay, so the x cubes, that doesn't really matter. But for this, originally when I had an x squared and I took the square root, then it has to be plus or minus the square root. If I took the nth root, all right, of something x to the nth power, well, if that n was odd, then I don't have to do plus or minus. But if it is even, then I do have to do plus or minus. So the question is, why? Well, basically, it has to do with this. If I'm starting with an x squared here, remember, taking something squared is an operation, right? But you essentially have to look at the domains of these. If I have something like x squared, just think about the graph of this. The graph of an x squared is a parabola, and the range goes from all the way to the left to the right, which is all real numbers. However, the square root of x is really only defined, at least in the real numbers, in the first quadrant, or where x is greater than or equal to 0. You could also say where y is greater than or equal to 0. All right, and so what's the reason here, right? Well, remember that if over here, if I have x squared is equal to 1, well, x could be 1 because 1 squared is 1, or it could be -1. -1 squared is +1 as well. However, over here, if I have the square root of x is equal to 1, well, the square root of +1 is 1, but the square root of -1 is not 1. It's a whole another set of numbers called the imaginary numbers. In fact, that is the definition of I. So in other words, the reason why I have to take this plus or minus is, imagine you're starting right here at this x squared. This x squared right here has a domain of all real numbers, all the negatives and the positives, right? That's what this operation has its domain over. However, when I take the square root, the positive square root, right, then that is only taking care of the positive numbers, or where the x is greater than or equal to 0. But what about all the negatives? I'm missing those. So that's why we have to add that negative in there. So it's not just plus the square root, it is also negative the square root. So that's why it's plus or minus the square root. All right, and again, you can apply this rule, or you have to apply this rule, I should say, whenever you're taking the nth root of x to the n power, but if that n is, that index is even, okay, then you have to use that plus or minus. Okay, so let's go ahead and take a look at what all this means graphically. So here we go. So say I'm starting here with this graph right here. This is the graph of y is equal to x squared plus 1. And if I went ahead and find the inverse, and we're going to go ahead and do that algebraically in a second, but just graphically speaking here, if I did the algebra, meaning I flipped the x's and the y's and then solved back for y, I would get y is equal to plus or minus the square root of x minus 1. This plus is taking care of the square root up here, the radical up here, right? And then the negative is its reflected version over the x-axis, right? Giving you this horizontal parabola, the full parabola here. So you can really see where that plus and minus comes into play. Now, of course, when we are taking an inverse, it's important to note that if we plot the line y is equal to x, then every value, every point on here is going to be reflected, meaning we're literally flipping the x's and the y's. You can grab any point on here and just switch the x's and the y's, and it will correspond to another point on its inverse. Also, if I go ahead and write this out, so if I write this out, I have f of x is equal to x squared plus 1. And if I wanted to write its inverse, it would be f to the -1 power of x is equal to plus or minus x minus 1. Now, one thing to note here is that domain and range become really, really important. It's not actually that important in this particular problem, but you'll see in the next one. But I want you to note that this is also the case whenever you take an inverse. For the original function, if you have the domain and the range, in this case, the domain, the x values for this y is equal to x squared plus 1, that is all real numbers, right? I can go forever to the left and to the right and get x values to input into this function. And the range is y is greater than or equal to 1. So I'm only getting y values back that are at 1 or above, right? Now, if I take a look at the inverse, what are the domain and the range of the inverse? Well, the x values are going to start here at, if I go all the way to the left here, it's going to start at +1 and then go all the way to the right. And for the y values, well, I can go, I'm getting y values for whatever I plug in for the x. I'm getting y values all the way from -infinity all the way up to +infinity, so all real numbers. Now, what's important to note is that for the inverse function, the domain and the range switched. For the original, we had a domain of all real numbers, and for the inverse, the range became all real numbers. And for the original, the range was y is greater than or equal to 1. Well, for the inverse, the domain became x is greater than or equal to 1. And so this is always the case. Now, usually you don't actually have to write the domain and range because it's automatically taken care of when you're graphing these. However, I'm going to show you another example where it's not automatically taken care of. So what if we started with this function, a radical, namely a square root, or the square root of x minus 1. Well, in this case, we only have half of this parabola, right? And if I algebraically figured out what the inverse is for this, which we will do in a second, then I would end up with y is equal to x squared plus 1. But when you graph these, this does not make sense, right? There are definitely points over on this parabola right here, actually, this half of the parabola, that don't appear in this original. So how do we take care of this? Let's go ahead and look. So what we're going to do is we're going to, I don't know if you noticed that flipping there. So we're going to flip, we're going to put a restriction essentially on here. We're going to say, oh yeah, it is x squared plus 1. That's what it is. However, only for, in this case, x is greater than or equal to 0. So we're going to place that restriction of the domain on there. So let's go ahead and take a look at what this looks like notation-wise. So if my original was f of x is the square root of x minus 1, my inverse was x squared plus 1. But again, that is not really the inverse of this because it has way more. Let's go ahead and take a look at that original, right? This right here is not, in fact, the inverse of this. We have to go ahead and restrict it, only getting a specific piece of that function. So in this case, we typically restricting the domain if we can. You could do the range if you wanted to, but anyway, and it would actually work. But anyway, in this case, we can just say, okay, well, only for x is greater than or equal to 0. So this fully is the inverse of this function f of x. Now, there are other pieces to this, right? If I wanted to fill out the domain for the original and the range for the original, you can see, well, the domain in the original, this one right here, we have x is greater than or equal to 1, and that becomes the range. Y is greater than or equal to 1, as you can see right here, and it holds true. And then same with the range of the original, y is greater than or equal to 0. Well, our domain becomes x is greater than or equal to 0. So typically, we would just list the domain if we can get away with it, which usually you should be able to actually all the time. So anyways, however, you could also write the range if you really wanted to. So when you're first starting out doing these problems, it was really beneficial to probably write down the domain and the range and then just flip them. Okay. All right, so let's go ahead and do some examples here. Okay, so here's the first example we have to work out. And so we're going to find the inverse of the function g of x is equal to the square root of x plus 2 all minus 1. All right, and so let's go ahead and do this. So the first thing I really want to do is I kind of want to sketch out a graph of this. The graph is not really a part of this problem, but it will help me, right? So if I wanted to graph this, well, remember the square root is going to look something like this. But in this case, we're going to go down 1 and then let's see here, left 2. So left 2, down 1. So it's going to look like this. And 1, 2, 3, over here like that. Okay, so here we are. So this is what our graph actually looks like. And so the reason why it's helpful to graph this, and by the way, sometimes I'll put on the line y is equal to x here as well, just to give myself a, just a little marker or whatever, so I know kind of where I'm going at. Actually, technically speaking, I could literally go ahead and just plot these points and then figure out what this graph is, and that's my inverse, which wouldn't be that hard to do. But let's go ahead and do this algebraically. All right, so so why did I graph this? Well, first of all, I wanted to find the domain in the range. So the domain, I'm just going to mark it up here. The domain is going to be x is, in this case, greater than or equal to 2. I'm sorry, negative 2. And the range for the original here is going to be y is greater than or equal to negative 1. And I know that for my inverse, I'm simply just going to flip the domain in the range. Okay? All right. Anyway, so let's go ahead and find the actual inverse here. So what are the steps of finding this inverse? Well, remember, this is y is equal to the square root of x plus 2 minus 1. And what I want to do is flip the x's and the y's. So all the x's become y's and all the y's become x's. So I have x is equal to the square root of y plus 2 minus 1. You can put a little dotted line here if you want. All right, and then let's go ahead and solve algebraically. So I'm going to add 1 to this side. So x plus 1 is equal to the square root of y plus 2. Now I'm going to go ahead and eliminate this by the square root by squaring both sides. So that leaves me with x plus 1 squared is equal to, and then this y plus 2 pops out. And then finally I'm going to subtract this 2 off here. So x plus 1 squared minus 2 is equal to y. Now I've isolated the y, and so now this here is my inverse. Now let's go ahead and write it out how it should be. It should have a name. Remember, this original was called g of x, so the inverse is g to the negative 1 of x is equal to our actual inverse here of x plus 1 squared minus 2. And I could actually go ahead and, again, just simply take the range here of the original and convert it over to the domain of this. So instead of y is greater than or equal to negative 1, it is now going to be x is greater than or equal to negative 1. And let's just go ahead and see if this actually works. I'll use a green here to graph this. So here we go. So we have the graph of x squared is going to look something like this, right? Whoops, that's a pretty terrible parabola, but something like that. But this is going to get translated, let's see here, down 2 and then to the left 1. So down 2, left 1. However, and so if I graph the whole thing, it would look like this. Something like that, right? However, in this case, we're only interested in where x is greater than or equal to negative 1. So it's only this side here. Whoops. Only the right-hand side. And you can see here very clearly that this this blue graph and this green graph, representing the inverses of each other here, they definitely are reflected over the line y is equal to x. You could also say where y is greater than or equal to negative 2, negative 2 if you wanted to here, but it's really not necessary. The x is all we really need in order to restrict our actual graph to appropriately. Okay. Anyways, so let's go ahead and put a little box around this. This is our final answer. One other way to check this, by the way, is to plug these into each other. If I plug g, the inverse of g into g, and vice versa, then those should go ahead and simplify down to just x. Okay, so that's how you can always check your work. All right, let's do one more example. All right, so here's our second example. We're going to find the inverse of h of x is equal to x plus 2 squared minus 1. And so again, I'm going to go ahead and kind of sketch a graph here first, and just to get the domain and the range down, and then we'll go ahead and do this algebraically. So of course, this is the parent function is y is equal to x squared, and so that would, like I said, look something like that. However, we are going to go to the left 2 and then down 1. So right here. Is that the same as the one before? Can't remember. But anyways, in this case, though, we definitely have a parabola, right? So here's our original. And then let's see here. So up 1 over 1, and then over 2, up 4. 1, 2, 3, 4. So here we go. So here's our original graph. Let's see if I can draw this halfway decent. All right. Good as it's going to get for me. And so let's go ahead and find, let's go ahead and list the domain and range first of all. So the domain and the range. So the domain is going to be all real numbers. I can go forever to the left and the right. So we'll say x is equal to all reals. And then the range, though, is going to start at negative 1 and go all the way up. So that is y is greater than or equal to negative 1. All right. Now, let's go ahead and we'll find the inverse of this. So here's our original function. I'm going to go ahead and straight to flipping the x's and the y's. So this is going to be x instead of y on this side is equal to y plus 2 squared minus 1. And then let's go ahead and we're going to isolate the y. So I'm going to go ahead and add 1. So x plus 1 is equal to y plus 2 squared. And now in order to wipe out that squared, I need to take the square root of both sides. But this is where you need to be very careful. Whenever you're taking the square root of something squared, then you have to have plus or minus. And it actually doesn't matter if you put it on the right or the left. Typically, we put it on the other side because it will end up moving over there anyways. But anyways, so always put your plus and minus. So that's what we are ending up with here. So we have plus or minus the square root of x plus 1 is equal to, and then in this case, y plus 2 pops out. And then I'm going to subtract 2 from both sides. So I'm going to say plus or minus the square root of x plus 1 minus 2 is equal to y. And now let's go ahead and write this the way we need to write it. In this case, it's h of x is the name of this function. So we will say, oops, I lost my pen there. Let's see if it comes back. There we go. H to the negative 1 of x for the inverse, symbolizing the inverse, is equal to plus or minus the square root of x plus 1 minus 2. Now, the question here is, do I need to list my domain and range restrictions? Now, you definitely could, but many times the graph will handle it itself. In this case, the graph will handle it itself, so or the function itself. So I don't actually need to list these domain and ranges or restrict them in any way. So let's go ahead and graph this just to show that this is in fact the it matches. I guess it's reflective over the line y is equal to x. So let's go ahead and graph it. So let's see here. So the square root is going to look like this, right? Something like that. But we are going to go left 1 and then down 2. So left 1, down 2. And then we are going to shift all of these. So this is plus or minus. So here's my, whoops, not that one. Here we go. There's the positive side, and there's the minus, the negative side. And let's go ahead and graph these or connect these. Okay, and there you go. You can definitely see that these are reflected over the line y is equal to x. And then if you wanted to restrict this further, or I'm sorry, not restrict it, but if you wanted to check it further, then you could go ahead and plug in the inverse of h of x into h of x and vice versa, and you should get x back after simplifying. Now, really important here again, note that I did not have to list any domain and range restrictions here because I am listing the full graph. The full graph of this is or the full function of what I got out of here is indeed the inverse. Okay, so no restrictions were required. All right, really where you're looking at listing those restrictions is pretty much anywhere where you have like this half of a parabola, essentially. Okay, so anyways. All right, guys, so there you go. There's a little lesson on finding the inverses of radicals. Now, I want you to note that we did only cover square roots in this particular example. However, you can have cubed roots, fourth roots, fifth roots. So we're going to have a little mini lesson after this, just talking about how we handle those situations, which actually those are much easier. Okay. Anyways, hopefully you found this lesson helpful, and I hope to see you in the next one.